Good afternoon, everyone. My name is Mark Lavega. The area I'm handling is calculus. I'm in my second year, software engineering. I've been in this group for a year now. Yeah, so what I'm looking at today is multivariable calculus. What most of you are familiar with is single variable. Let's handle calculus 1 and 2, whereby you're dealing with functions that take in one input. Let's say you have a function f of x is equal to x squared. So these functions normally take in one input, what we call the variable. So now we want to look at multivariable functions. Let's say f of x, y. They could be 3, 4, okay, or as long as they are more than one, that's a multivariable function. So let's step 1 with 2 variables. Let's say x squared plus y squared. So normally these take in 2 inputs, but the output is always one outcome. So x can be y and y can be 2. The resultant will be, so f of 1, 2, 1 plus 4 is equal to 5. What you know that the outcome is always 1. So now when we go to derivatives, here it is always direct. I'm sure most of you have a background in mathematics, A-level mathematics. Here it's direct. Here we deal with partial derivatives. Yeah, so in partial derivatives, you first deal with one variable, but you take the other one to be a constant. So let's continue with that function. F is equal to x squared plus y squared. So what we're going to do, we're going to first get the partial derivative of this function with respect to x. So it's more like when you write x6 of this function with respect to x. So here, x is the variable that you're dealing with, it's 2x. Then y in this place it's a constant. So when you differentiate constants, you get 0. And then now getting the partial derivative of this function with respect to y. In this case, the x is now a constant. When you differentiate a constant, you get 0, and then the y squared to y. I think you're together to this point. So now that takes us to finding the gradient. So gradient normally with the single variable functions, we just let the first derivative to be equal to 0. Then you get the sorry, it's not the input. We take this x to be equal to 0. In this case, it will also be 0, but the gradient we take it to be the point whereby the first derivative, sorry, the partial derivative with respect to x. Sorry, this is f x, then respect to y. However, in these cases, we take the values of x to be equal to 0. Sorry, of the variable. So here I think we got 2x and 2y. So when you substitute for 0 in both variables, the gradient is equal to 0. Yeah, then assuming these two variables depend on an external factor, let's say t, finding the gradient, this with respect to t is, I think that's chain rule. And if you are to chain it, let's say x and y are depending on another factor t. So now will be equal to E F, yeah, then hence dx. Yeah. Then for delta y it will be df dt times dt. It's just an expansion of this. Yeah. So gradient normally is denoted by, I think this is an inverted triangle. I think delta f, taking f as the function, f x of y, so x into x and y. So visualizing them, the single variable function gives us a curve in a 2D space. A 2D space is like a graph with two axes, x and y. And then a function with two variables, say this one, gives us a surface in a 3D space. Yeah, it's like a plane. Then so what partial derivatives tell us is that if you're moving in the x direction, yeah, the function is either going up or down, but in that direction, the x direction, and also how steep it's going. And then with respect to y, means that you're moving in the y direction, either up or down, but in that specific direction, and also how steep. That's like, should I say, movement. If you're moving looking at, okay, like on this surface, are we moving left or are we moving right? And then on the other axis, are we climbing or are we descending? In that sense. Yeah? Time. So that was a brief introduction, and how we apply them, we shall look at them next week in our next meeting.
Thank you.